On its very first job, this prototype 475 established production rates as high as 1,200 tons of shot rock an hour. Very early in 1967, the first production 475 went to work in a strip mine in Kentucky, digging out a 12-foot seam of coal nearly 100 feet below grade. Replacing a 5.5-yard swing shovel, the 475 quickly established production rates of 700 tons per hour. In February of 1967, production machine number 2 went on the job for a coal company in West Virginia, removing overburden on a mountainside to get at a coal seam. The third Michigan 475 also went to work on a mountainside stripping operation. And the word began to get around that the new 12-yard Michigan was moving one heck of a lot of material. This job also proved that the Michigan was a bear for rock work, something that most people had thought was the exclusive province of the swing shovel. Then, for the first time, a new concept, load and carry, was built around a large tractor shovel. A quarry in New York State was set up for the 5th Michigan 475 to load out shot rock and carry it to the portable crusher. The fame of the 475 spread, and the application for the machine broadened. Machine number 10 did stockpile loading in Gary, Indiana. Machine number 12 was put on a shot rock job in Vermont, loading out highly abrasive granite. Difficult blasting conditions left the material interlaced because of the rock formation, but even so, the production rate averaged 1,000 tons per hour. A contractor in San Diego with a big cut and fill job for an interstate applied the 14th 475. Tailoring the width of the bucket to match the size of the triple haulers permitted him to load the 3-haul units in 3 passes. He quickly established a production rate of 1,500 tons an hour. A very large contractor in Northern California, who was also highly innovative, took the 28th Big Michigan. On a 2.3 million yard cut and fill portion of an interstate, he used dozers to make the cut and the 475 to load out 120-ton bottom dumps. Even though the 475s were establishing outstanding production rates of many kinds of jobs throughout the country, some users were beginning to think about a tractor shovel with even more capacity. What was happening was that the concept of a truly big tractor shovel doing swing shovel work was becoming firmly established. Owners were finding out that the capital outlay for a big tractor shovel was about half that required for a swing shovel with the same productivity, and that the per yard cost was lower than it had ever been. Machine number 32 went to work loading out fill for a 12 million cubic yard earth dam in Texas. While the machine loaded out 50-yard bottom dumps in well under 2 minutes, it became increasingly apparent that contractors, road builders, and mining companies really did need and would buy a much larger tractor shovel. By the time over 200 475s had been bought and put to work, Clark had completed the engineering and started the fabrication of a 24-yard tractor shovel. The fabrication of any prototype machine is a slow and painstaking process, and particularly so for a machine the size of the 675. Here, the lower steering pivot subassembly is eased into position alongside a mainframe side plate. The second side plate is carefully positioned. It is fabricated out of 3-inch plate steel. The weldment setup is done very carefully, since many of the major components are pinned together during field erection. Any slight misalignment would make final assembly very difficult. This is the rear cradle axle frame support to which the rear drive axle is attached. When the components are checked out and found to be absolutely square and in perfect alignment, they are welded in place. The upper steering pivot subassembly for the rear half of the machine attaches next. This is very exacting work because the 2 pivot points are 7 feet 10 inches apart and must be perfectly aligned. The finished 24-yard bucket for the 675 was to weigh about 25,000 pounds and had to be tough enough to stand up to highly abrasive rock. A structural member is carefully put into place and tacked down on one end. Weld clamps to both locate the member and hold it in place for welding are tightened down, and then the part is welded in place. Next, the bucket ribs to which the bucket push rods will attach are carefully placed into position. This also is exacting work, since the bucket linkage push rods are to be pinned to the bucket. The front half of the main frame turned on its side to facilitate flat position welding. The engineers were fully aware of the structural loads to be imposed on the machine components, so it was absolutely imperative that every weld be of optimum strength. While fabrication of the two frame halves and the bucket was taking place, the drive axles were being fabricated and assembled in Clark's automotive division. These 23,000-pound monsters were the largest torque proportioning differential planetary drive axles ever built by any company. Here the wheel hub is being attached to the end of the axle housing. Then the Planet Drive ring gear is carefully installed and bolted to the massive wheel hub. The enormous Planet carrier assembly went into place next. Next, the differential carrier assembly was lowered carefully into the banjo housing of the axle and bolted into place. Every bolt is torqued accurately, since the proper torque for every bolted assembly is highly critical to long machine life and helps prevent downtime. The 4-inch diameter axle shaft is carefully installed to mate with the spline in the differential, followed by the sun gear, which completes the power flow from the differential to the wheel hub. Next, the disc brake caliper assembly was carefully maneuvered into place and bolted down. In planning and designing the new 675 tractor shovel, the Construction Machinery Division relied heavily on the skill and expertise of Clark's Automotive Division. Even though this division over the years had produced tens of thousands of transmissions and axles, the 675 axles had new features which required testing. Therefore, it was thoroughly wrung out in Clark's corporate engineering laboratory on a large dynamometer setup. Tests for quiet running gears, for torque bias in the torque proportioning differential, for proper lubrication, for total power transmission efficiency, because power wasted in the powertrain can't be used to do work for the customer. Power for the 675 was to be generated by two 16V Detroit diesel engines sitting side by side, each driving its own Clark torque converter. The two torque converters in turn would feed into Clark's giant power shift transmission. Here, the second engine is being lifted into place. At one point in the fabrication of the 675, it was time to test out some of the main components for the tremendous stress loads which would build up in operation. One of the components so tested was the boom assembly. The procedure is to attach strain gauges in areas which have shown stresses, as evidenced by cracking of the brittle stress coat lacquer. The strain gauges are then wired through a junction block to the automatic printout strain recorder, and components are hydraulically jacked to simulate working loads. By checking the readouts, the engineers are assured that there is plenty of reserve strength in every vital structural part. After successfully completing the dynamometer test, the front axle is ready for assembly to the front half of the main frame. To facilitate field direction and provide proper strength, the axle assemblies are pinned to the main frame. The pins are held in place by steel lock plates which fit into slots cut in the end of the pins. After months of arduous and painstaking work, the time came to start running the 675, with the first operator chosen by lot, since every engineer and technician wanted to be the first to operate the world's largest tractor shovel. Careful check of the 4 boom hoist cylinders at full height. Reverse. Turn. Ahead. A hydraulic hose check by the engineer who designed the machine. A check of system pressures by a technician from the automotive division. Some last-minute instructions from the Vice President of Engineering. And finally, it was just human nature to drive a 475 alongside for an eyeball comparison. Quite a jump, from 12 yards to 24 yards. The 475 owners had asked for a larger machine, and Clark had really come through. The prototype 675 was to be field tested in a quarry in Tennessee and had to be disassembled for shipment. The machine components filled 3 railroad flat cars, or 8 large truck trailers.
Starts in a threader, so that's the lopper down. Yeah, lay down this left. Now watch it outside there, but yeah, coming right on home, buddy. Looking good. Looking real good. Take it right on in. I'll rig right here where you can tie to it. Looking real good right now. Yeah, let's just keep right on going with that. He can swing now any time to make a job. I think what he's doing now. Have to look through there and see it now. There it is. That's pretty close. Okay.
Type 675 went to work. We talked to Dick Shirley, Vice President of Vulcan's Mid-South Division, on the left, and J.B. Lambert, Operations Vice President.
This quarry is located about 15 miles south of Nashville, Tennessee on I-24. We're crushing stone for I-24 from Nashville to Chattanooga. Our plant is located in a limestone formation. We have set up an operation to produce approximately 1,200 tons per hour. We're now operating with 2 front-end loaders loading into M30 Mack trucks, 4 of them. We plan to replace the 275 Michigan front-end loader with the 675 to load and carry to the primary crusher, eliminating the trucks. We plan to use this with the 475, the 12-yard Michigan, and replace the 4 whole trucks. We have approximately 1 million tons of stone produced here from this site.
And switch over they did, eliminating the Michigan 275 tractor shovel and 4 haul trucks. The 475 and 675 loaded and carried all of the material to keep the entire plant running. The machines get a load of shot rock at the face and then have a level run on the quarry floor of between 210 and 250 feet, depending upon where they get their load. There is a 550-foot haul up a 17% grade to the crusher. The 675 averaged 36 tons per bucket load. At the top of the ramp, the load is quickly dumped into the crusher, and the machine turns to go back down into the quarry. At the time this film was shot, the 675 and 475 together were producing at an overall operating efficiency of 93%. 2 machines and 2 operators equaling the previous production of 6 machines, 2 tractor shovels, and 4 trucks, and 6 operators. Tractor shovel load and haul applications are inherently highly efficient, since the unit doesn't have to wait for any other machine which may be part of the operation. It just keeps loading, hauling, and dumping. In the average loading out setup, the tractor shovel often waits for an empty truck. And trucks wait for a chance to dump at the grizzly because they get bunched up. It's the accumulated non-productive time that reduces efficiency and increases per yard costs. The 675 is really big. Nearly 50 feet long, weighs 350,000 pounds, and has an operating capacity of 72,000 pounds. It's built for rock work with a breakout force of 148,000 pounds. There are 4 10.5-inch boom cylinders and 2 10.5-inch bucket cylinders to get heaping loads fast. The powertrain consists of 2 Clark torque converters, a Clark power shift transmission, 4 speeds forward, 4 speeds in reverse, and Clark all-wheel drive planetary axles. The 675 has a centralized lubrication system, programmed to automatically lubricate every moving part except prop shafts. This reduces servicing time. The cab is pressurized with filtered clean air, heated in winter and air-conditioned in summer to keep operator efficiency at a high level. It is sound insulated as well. And the operator has good visibility, going into the face, on the carry part of the cycle, and when dumping. The Michigan 675, continuing proof that Clark Equipment Company is alert to the equipment needs of its customers. Clark has the skills facilities, experience, and imagination to create new concepts in materials handling.